Greetings everyone and welcome to this new video on how to perform logistic regression in R. In this video we'll learn how to write the correct syntax to perform simple, that is univariate, and multiple, that is multivariate logistic regression in R. These are a few libraries that we need to load. I've written brief descriptions about each library, and for the purpose of this tutorial we'll be using the Titanic dataset. I'm sure recurrent viewers are familiar with this dataset because the same dataset was used while doing logistic regression in JASP. But for the new viewers, or to re-jog your memory, this is a dataset which contains data on the survival of passengers on the Titanic. And we have three important variables, predictor variables: the passenger class, here P class, first, second or third class, the age of the passenger, and the sex of the passenger, so male or female. And the last column indicates whether the passenger survived or not. So let's go ahead and load this data set on an object df. Let's omit all the blank columns. Any.omit is the function for that. And let's create a descriptive statistics table. So this TBL underscore summary function from the GT summary package is does just that. It's an amazing package, the GT summary package. And specify which columns in the data set you want. This is the syntax to do that. And specify we want to group between those who survived and those who did not. So the by argument allows us to do that. The add overall adds a column, an overall column, in addition to the group survival status. And add P adds by default non-parametric tests like the Wilcoxon rank sum test, also known as the Mann-Whitney test, the chi-square test, and the Fisher's exact test. So let's do that. Let's see the T. So prima facie, 0 indicates death and 1 indicates survived. So prima facie we can see that passenger class and sex appear to be associated with survival. Age is not. Although the interquartile range suggests that those who survived might be younger, but let's see about that later. As far as the passenger class goes, we can see that those in the first class were more likely to survive, or the passenger class was associated with survival. You can see 44% first class survived, whereas 54% third class did not. And the sex, 70% of females survived and almost 85% males did not. Right, so now that we have a little bit of insight into our data, let us go straight into modeling. We'll come to the assumptions in a bit after we model our data. The first three models, let's focus on creating simple univariate logistic regression models. So the GLM function helps us to create a generalized linear model. Remember, the LM function was for linear regression. The GLM function is for generalized linear models, and we can specify that we want to do a logistic regression by specifying the family argument as a binomial. This syntax is very similar to and akin to how you would perform a t-test or a linear regression. The outcome variable, the binary outcome variable, is on the left hand side of the tilde, and the predictor variable is on the right hand side of the tilde. This is the tilde. So the first model, we are seeing the effect of class, second the effect of age, and third the effect of gender, sex. And the report function from the report library helps us to, as the name suggests, get detailed statistical reports. And the TBL UV regression function, again from the GT summary package, helps us to get publication ready tables. We need to specify which variables you want, the method, the outcome variable, and whether we want to exponentiate. Since in R we get the logarithm of odds ratios or log odds ratios by default, we need to specify explicitly that we want the exponential of that log odds ratio, that is the odds ratio simply. So let's do this, and we can see in this table created by this TBL underscore UV regression function that passenger class, second and third class, the odds ratios are less than 1. Confidence intervals do not cross 1. So passengers from the second class were 15% less likely to survive than passengers from class 1, and passengers from third class were 31 times less likely to survive, or 31% less odds of survival than passengers from the first class. Both are significant. Age apparently is not associated with survival yet. Let's more about that later. And gender, sex, males were 42% less likely to survive than females. Significant p-value. And let's check the explanatory power model fit. 10% variance for class. It's not pretty good. For age, the R squared is extremely low, and for sex we have 30%. Pretty good. Sex did explain the model pretty well, and if you're familiar with the story of the Titanic, this makes sense, right? I mean, females and children, first to be first on the boats. So this conforms with the story that we all know. This explains the model quite well, 30%. Right, but all of these are univariate models, simple models. We want to find out how all of these variables put together influence the outcome. So we want to find, so these are univariate models. They do not take into account, or they do not adjust for other variables. So the model on class does not account for age or gender. Similarly for the rest. So we want to create a model which accounts for all these variables together, and that's why we will create a multivariate logistic regression model. A very similar syntax, only just add the predictors with plus signs together on the right hand side of the tilde. Store the model in an object fit all, and get the report. Now the TPL underscore regression function from the GT summary package gives us a very similar table to this one. Specify exponentiate is true to get odds ratios, and the TPL underscore merge function actually merges any table that we want. So we want to merge the univariate and the multivariate tables because it's better to it's good to see both the univariate and multivariate models side by side together, and this does exactly that. So let's run this chunk of code and let's see. So this table, wow, what are we seeing here? Age is now significant, and not just significant with a p-value of less than 0.001 and odds ratio of 0.96. So age indeed is significant predictor for survival on the Titanic. Specifically, for each year increase in age, survival decreased by 4%. So as you get older, or as passengers on the Titanic, for each year, the passenger who was 1 year older than the other on the Titanic had 4% less probability of survival than the younger participant, adjusting for class and gender. Very important discovery, and these such models uncover hidden patterns in data which you would normally not have found here in simple association tests or univariate models, in fact. So interesting, the effect of gender and class is exponentially increased with significant p-values like before. But this was the interesting finding that I was hinting at a while ago. And if we try to see the explanatory power of the model, it is now 40%. 40% uh, prediction, or 40% explanation of the variability in the model. That is a pretty good fitting model. So altogether, passenger class, age, and sex explain 40% of the model's variance. That is how you interpret R squared. And now that we have R squared, let us assess one more model performance metric, that is the area under the receiver operating characteristic curve, AUC ROC. And this ROC function from the PROC library enables to do just that. And AUC closer to 1 indicates a good fit, better performing model. This is 0.85, which is pretty good. And if this was a 90-degree or a rectangle, this would have been a perfect model fit. In theory, it is possible. In practicality, there is no model which is a perfect fit. So this is a pretty good model. It almost conforms to the perfect performing model. Pretty good. So this is yet again a reiteration that the model that we have fitted is pretty good, and all of these variables explain the outcome pretty well. So if I were a cruise ship company, or a CEO of a large cruise ship company, and I was to retrospectively study which factors were associated with survival in case of a disastrous outcome, this model will let me know, okay, so passenger class, right? So first class more likely to survive. So I would likely want to make provisions so that the second and third class passengers were not left out. Age, I would probably want to make provisions where elder people are given extra provisions so as to enable them to survive. And sex, that is a controversial topic. I don't want to go into that topic, but ideally I would want both of the sexes to survive with equal probability. So now that we have interpreted the model, let's come to the assumptions for regression. And there are multiple assumptions, and the first one is very obvious, a binary response variable that we do have, survival yes or no. Independence of observations, each passenger is unique, that is also true. Multicollinearity among explanatory variables, you don't want multicollinearity. And what I mean by multicollinearity is one variable should not be overly correlated with the other variable. If we have two or more variables that are correlated, then I would ideally want a combined variable and not keep three different variables. Ideally a combined variable, or remove the other variable or variables which I don't feel are which I feel don't contribute to the model a lot. I'll just keep the most important variable. So the VIF, or the variance inflation factor, is a metric to assess that, and the GVF, generalized variance inflation factor, should not be, as a rule of thumb, more than 5. And here we are pretty good. It's all of them are less than 5. So none of the variables are overly correlated with one another. That's pretty good. So this assumption is also met. No extreme outliers. You typically do that by checking Cook's distances. And here we see these points indicate, all of these points indicate each individual observation number, and I can see 3 data points which might be considered to be overly influential. 25th data point, 293, the 293rd data point, and the 1200 and 9th data point. Ideally, I would want to remove all the 3 from the data set before I run the model. This tells me that. So if I were to refine my model, I would remove these 3 data points. And the 5th one assumes that there is a linear relationship between the explanatory variables and the logit of the response variable. So in linear regression, as we all know, the outcome is linear or continuous. a numerical variable. In logistic regression, the outcome that we specify is binary. Why is it called a generalized linear model, the GLM, right? Why is it called a generalized linear model? So we try to convert the outcome into a linear vector or a linear variable, probability variable. So how do we do that? We take the logit function, and this essentially is a linear variable, numerical variable, which converts probabilities of the outcome occurring into numerical variable. So this is the function to do that, logit. And let's plot one predictor variable, age, with logit to see if it's linearly, there is a linear relationship or not. And yes, there is a linear relationship. We can see this blue line and pretty narrow confidence interval. So this is pretty good. So I would say that this assumption is met. And lastly, whether we have a sufficient sample size. So ideally, what you would want to do is calculate the sample size a priori. Now, for this sentinel event of the Titanic, there is no way where you could calculate the sample size a priori, right? So a posteriori, you would want to see whether the power is there is sufficient power to run a regression model, or you can just go by following this rule of thumb. Now this is specific for logistic regression, but this is a rule of thumb. This is not a formal power calculation, mind you, but this still is a practical working formula. So tan into number of explanatory variables, in our case it's 3, divided by the expected probability of the least frequency outcome occurring. What is this? What is the expected probability of the least frequency outcome occurring? So let's go back to this table, and survival is the least frequently occurring outcome, 313 as compared to 443. So to calculate the probability, we this is the numerator divided by 313 divided by 443 plus 313. That, using that, we get the probability for this survival occurring. And this is just that, this formula denotes just that, 313 divided by 443 plus 313, and running this formula, we get an ideal sample size to run this regression would be 73. And how much do we have? N row 756, almost 10 times the number of observations that we would have needed. So pretty good. This assumption is also met. And looking at the assumptions, looking at the model fit, looking at the ROC curve, I would say this is a pretty good model. Would I trust this model? Absolutely. Maybe remove these 3 overly influential variables, but as far as trusting the model goes, pretty good model. I would use this model in making business decisions or healthcare decisions or something like that, based on the biologic plausibility or the model performance metrics themselves. So this was all about how to perform logistic regression in R, both univariate and multivariate. I hope you enjoyed today's video, and I'll catch you all in the next one.